So our mathematician is Blaise Pascal, who was born June 9th, 1623 and died in 1662 in Clermont-Ferrand, France. When he was young, his father homeschooled him, and he made math a forbidden topic for him because he wanted him to focus on more classical studies like language and the arts. But because the topic was forbidden, Pascal secretly started learning math, and it sparked an interest. In 1655, he published the triangle arithmetic, which was the foundation of probability. He's most famous for his Pascal roulette, which is the little wheel machine, and it's the black and white machine that you see while gambling and playing, I don't know, blackjack, I think. But you just spin it, and it the circle goes around.
Roulette?
Yeah, that's it. Roulette, yeah. So that's what's still used today the most, which is called the perpetual motion machine. Before it was called the little wheel or the roulette.
Wheel.
Yeah.
Mind over matter, does it matter to any of us? Don't change the subject, I'm heavy on your love.
Pascal's triangle wasn't actually invented by Blaise Pascal. He actually came up with the idea when a French nobleman came up to him and asked him a question about gambling, and when he talked to one of his other mathematician friends, he kind of came up with a book about the properties and applications within the triangle to use it in a gambling sense. But the triangle was actually invented hundreds of years before he was even born by Chinese and Indian mathematicians. And the earliest depiction of the triangle was the Chinese, where they came up with a book called The Precious Mirror of Four Elements, and they had pictures of the triangle, but it was in Chinese numerals, and it kind of talked about the binomial coefficients and how the triangle actually worked, and that's basically where it stems from.
This red is Pascal's triangle. Each number is the sum of the two numbers directly above it. So this 3 is the sum of 1 and 2. For this 10, it's 4 and 6, and so on and so forth. There's a couple of interesting elements, and these aren't even all of them. The sum of each number in these rows are twice the sum of the one above it. So the sum of 1 plus 2 plus 1 is 4. Then here you have 2, and then down here you have 8. Or you can also just represent it with 2 to the n, where n is the row number. So for here it would be 0. 2 to the power of 0 is 1, and so on and so forth. Also, we have this representation of powers of 11, where here would be 11 to the power of 0, 11 to the power of 1, and then 11 squared is 121. And so on and so forth. Now, once you get to the point where you have double digits, you kind of have to do some trickery to where you move this, the leftmost digit over 1, and you'll still end up with, 11 to the power of 5 in this case. And then if you lay it over a square grid, and you start from the top left, and if you only move right or down, you can't go up or left, each square will show you how many moves it'll take you to get there. So for instance, 2, you have to go 2 spaces, or how many different ways there are to get there, I'm sorry. So for instance, here there's only one way down, or one way to the right. Now if you wanted to go to here, there's 10 different ways, 10 different combinations you can get to that square. So starting with a 1, and then imagining, a 0 on each side. In every case where there's not a number to the upper left or upper right, we add them, and we get 1 plus 0 is 1. And then from here we would go add another imaginary 0, and we would still get 1, but here we would have 2. And we continue on from there with our imaginary zeros and adding the numbers directly above them. And so on and so forth.